Now we're going to talk about chapter 16, aqueous ionic equilibrium. So we're going to use our knowledge, what we've been doing with ice tables, and we're going to apply it to buffers. And so I think the best way to understand these buffers is, hold on one second. I'm going to show you this video, but I just need to make sure you can hear it. All right, tell me if you can hear this.
Buffers are substances that minimize change in the concentration of protons.
It's very low.
Is it really low?
Yeah.
Let me try this.
All that means
Better?
really is that buffers prevent change in pH.
Okay. This is a great video. I love it. I'm trying to figure out this is as loud as I can get this. All right.
Buffers are substances that minimize change in the concentration of protons and hydroxide ions. All that means
I have no idea why it's not working. Oh, there we go.
All that means.
Hold on. Let me try this again.
All that means really is that buffers prevent change in pH. At the bottom of the screen is an example of a buffer. Buffers are made up of a weak acid, which is a proton donor, and its conjugate base, which is a proton acceptor. In this equation, we'll run in both directions to prevent dramatic changes in pH. It will run to the right in response to a rise in pH, and it will run to the left in response to a drop in pH. As an example of what a buffer does, we can use human blood, which has a buffer, and pure water that doesn't have a buffer. We'll take 1 liter of each of these substances and add 0.01 moles of hydrochloric acid. The addition of the hydrochloric acid to 1 liter of human blood will cause a change in pH from 7.4 to 7. The addition of hydrochloric acid to pure water will cause a change in pH from 7 down to 2. The reason that human blood prevents such a dramatic change in pH is because it contains a buffer. Now, if we focus on the illustration here in the center, we can illustrate how a buffer works. Human blood contains a buffer, and under normal circumstances, if we were to add an acid to human blood, initially the proton concentration of blood would increase. But since we have a buffer, it prevents that increase from being so great. The protons in the solution will combine with the conjugate base, as shown in the equation at the bottom. Those protons will combine with the conjugate base and form more of the weak acid, so that the proton concentration doesn't increase so much. Here in the flask, you see the protons moving and combining with the conjugate base, forming more of the weak acid. And this happens over and over again to prevent the rise in proton concentration and the addition of an acid. If we add a base, the opposite should happen. Under normal circumstances, the addition of a base will cause a decrease in the proton concentration. But the buffer will prevent that decrease from being so great. The equation will run in the opposite direction. On the left side of the equation, the weak acid will start to donate or give off protons into the solution. And that way, the initial drop in proton concentration will be overcome by the donation of protons from the weak acid.
Okay.
Buffers are substances that minimize.
We're not going to watch it again. Okay, so we're going to look at buffers. Sorry that I don't know why my volume isn't working. It's just the day of technical issues today. So we're going to look at buffers, and then we're going to figure out how to do pHs of buffers. So that's sort of what we're going to be doing today. So what is a buffer? A buffer is something that resists changes in pH when you add an acid or a base to it. So what they do is they neutralize the acid or the base that we add. But buffers are limited. We can overcome them. We won't get to the part where we overcome buffers today, but on Monday we'll definitely overcome buffers. So our blood has a very important buffer, right? If you think about all the food we eat like tons of acidic food, but we have this great buffer in our blood, like you showed, that makes it so the pH of our blood does not increase even though we eat really acidic foods. And the reason our pH does not increase, or sorry, our pH does not decrease is because of the buffer in our blood. So what is a buffer? So a buffer is, so there's either acid buffers or base buffers. So we're going to mostly concentrate on acid buffers. So acid buffers are just a weak acid and its conjugate base. So for example, its conjugate base, acetic acid, sorry, now my pen doesn't work at all. Every time I touch the screen, it just goes. All right. Okay, so you can see here that acetic acid is the acid and the conjugate base. We ignore the Na, right? Because Na comes from NaOH. It has nothing to do with our equation. So we just ignore, if it comes from a strong acid or a strong base, we ignore it. So all we care about this is the C2H3O2 minus. That is its conjugate base. So it's very Bronsted-Lowry heavy here. Maybe if I try to like unscrew my pen again. So buffers really work. It's all Le Chatelier's principle. And I really need to be able to write to show you this. So hold on a second. So remember Le Chatelier's principle, if you add something to one side, it goes to the other side. All right, my pen is not working at all. Okay, I'm gonna try and restart my PowerPoint one more time and see if I can get this to work. No, not working. Okay, so I'm just literally restarting my PowerPoint right now. Maybe that will help. Okay, so remember Le Chatelier's principle, like if you add, remember our buckets, our little bucket example we had, if you add to one side, it goes over to the other side. So that's what we're going to be doing with our buffers. So it works, it's just Le Chatelier's principle applied. How my pen works. Okay, hold on one second. Let me share this. Sorry. All right. My pen works. I know. Okay, so remember when we did Le Chatelier's principle? If you increase one, so for example, if we increase this, it will shift that way, right? So we're going to actually apply Le Chatelier's principle to these buffers, right? And so a buffer needs to have a weak acid and its conjugate base, significant amounts of both of those for a buffer to be effective. And so what happens is, if you add either an acid or a base, so if you add an acid, it's going to react with this base and shift it over here, right? Same thing. Yeah, I'm sorry, I don't know what's going on with my computer today. Same thing that happens with the bases. So let's look at this. Okay, so first let's add OH. So if we add OH here, it's going to react with the weak acid, right? Which is going to create more conjugate acid, right? Now, again, the buffer also contains a lot of our conjugate base, and they will react with the acid to make more weak acid. So after the equilibrium shift, the concentration of the H3O plus is kept constant. So even if you add acid, the pH won't change very much. So let's add some acid. So if we add acid, it's going to react with the conjugate base to make more weak acid. So we have negated the addition of the acid. So even though we added acid, the H3O plus reacted with the conjugate acid to create more weak acid. Okay, so how do we use this? So there's this thing called a common ion effect. It's basically just Le Chatelier's principle again. So if you add a salt containing the anion, whatever the anion is, right? We ignore the cation of that one, which is the conjugate base of the acid. It's going to shift the equilibrium to the left. So if I add this, the equilibrium is going to shift that way, right? Because this is going to react with this. So that's going to go down, and this is going to go up, right? Virtually not changing our pH. Okay, and it's going to change it, you're going to see, but it barely changes it. So let's look at this. Here's what a buffer does. Okay, so here we have just a 0.1 molar acetic acid solution. Its pH is 2.9. Here we have, and again, this Na means nothing to us. This is what we see. We just see the conjugate base, right? Now, when we add a good amount, and we'll talk about what a good amount is. We're just going to add an equal amount of this. You can see the difference in the pH, right? This is what a buffer is. So now what we could do is we could add acid or base to this, and this pH would not change very much. Okay, so I think that the easiest way to understand buffers is to do a problem with buffers. Okay, so let's look at this. What is the pH of a buffer that's 0.1 molar acetic acid and 0.1 molar, again, don't care about this, acetate? So the most important thing with buffers is, just like I told you before with the pH of our weak acids and our weak bases, is you have to be able to write the equation, right? So if we have a weak acid and we have it in water, what happens, right? We've done this. We get its conjugate. Right? If this is an acid, acids lose, bases gain. So now we have an ice table where we have 0.1 molar of this and we have 0.1 molar of this. So it's an ice table like we've done before, but this time, this is the only one we don't have. It's about zero. Not exactly zero, but about zero, right? So we just have two pieces to our ice table instead of one piece to our ice table. So again, remember, so this would be HA, and this is A minus, and this is obviously H3O plus. Right, so there's our HA and our A minus. I kind of want to get you used to seeing this HA and A minus. That's why I put these in our ice tables. So again, this is going to go towards our products. So this is going to be minus X plus X and our plus X, just like we've done before. So 0.1 minus X, 0.1 plus X, and X. And then we set up our equilibrium just exactly the same as we set up the equilibrium every single time. Our equilibrium expression does not change. It's just products over reactants. And of course, we don't put water in there. Except for this time we have the math that's a plane. That's really not fun. So we're gonna make a big assumption here. We're going to say that the amount of our acid and conjugate aren't really going to change that much. Remember, we're not assuming they're not changing. We're just assuming that the change is so small, it's undetectable, right? So that's what we're saying here. Okay. And here's my question. Is X is small going to work in this problem? comparing to what we've talked about before, looking at these, will it work? What do you think? That's my question for you.
No.
What do you think? Sorry, I couldn't hear you. Do we think X is small is going to work? Yes, I'm seeing lots of yeses. Yes. So we can assume that the change is going to be very small in this case. And so when we do that, now, okay, how did I know X is small is going to work? This is 10 to the negative 5, 10 to the negative 1, 10 to the negative 1. Again, and it's really this one that we look at more than the conjugate. It's this original concentration here. So it should, X is small, should work. Okay. So when we solve that, it makes it really easy because we just cross off our point ones and our Ka is our X because they are the same concentration. Best math yet. Okay, so if we check our X is small, we check the X is small just like we did with our weak acids and just like we did with our weak bases. We put them over our original concentration and it needs to be less than 5%. And again, we decided this would work because the difference between these is 10 to the 4, right? The difference between this number and this number is 10 to the 4. So it should indeed work. Okay, so now we want to know our pH. Here's our H3O plus concentration. So we just take the negative log of 1.8 times 10 to the negative 5, and we get 4.74. It should be like 4.74. It should have another digit here. Okay, so questions on this one. So remember, a buffer is just a weak acid and its conjugate base. So here's our weak acid, and here is our conjugate base. The only difference in this ice table that we just did and the ice table we've done before is we have both of these now. Besides that, there has been no difference in what we have done. No difference at all. We just have two values instead of one. Okay. Let's try another one. What is the pH of a buffer that has 0.14 molar HF and 0.071 molar KF? Again, most important part of this, you have to understand, like, what are we writing? You have HF, and we put it in water. We know HF is an acid that makes water a base. So that means this is F minus, right? That's this conjugate here. Plus bases gain, 3O plus. So when we do this, we're starting with 0.14 of this and 0.071 of this, right? So our equilibrium expression is just going to be F minus times H3O plus over HF. But remember, we want the pH, right? So we need this. So we must have a Ka. But they didn't give us the Ka. But they gave us a pKa, right? Remember, how do we go from pKa to Ka? If you don't remember what P means? P means take the negative log of it. So we just take 10 to the negative pKa, and that will give us our Ka. So we're going to do this. So first we're going to do our ice table with these. Then we're going to find our Ka. Then we're going to find our H3O plus concentration. Okay, so we wrote our equation. And again, this equation is really important. This is an acid, so our X is going to be H3O plus. It's going to go towards the products. So we got minus X plus X plus X. Now, how can we tell? So here's our equilibrium expression. We have to, in order to cross these off and be okay with crossing these off, we have to assume x is small. But remember, when we assume x is small, we need to compare this to our Ka, but we don't have a Ka. We have a pKa. So this is our first stopping point here. So we're good with this ice table because we've made so many of those. We know how to plug those in, but we need this number, right? That's what we need to figure out. We need that number. So what we do is, just like pH, we just take, I'll do it over here so you can have time to read. So we just take 10 to the negative p Ka, and that will give us our Ka. So 10 to the negative 3.15 will give us our Ka. And again, we need that Ka because we need to see, hey, can we cross these off? The only way we can cross those off is if x is small. We could try to cross it off and then test it, but you're going to find out it's better to know before you do the problem than to go back. So let's find our Ka. So we do that, we get 7.0 times 10 to the negative 4. Okay. Negative 4, negative 1. Our x is small will work. Sure, let's cross it off. Okay, so we do this. Our math becomes so much more lovely, right? This math is so nice. Not even any squareds here, just multiply by 0.14. Right, and then divide by 0.71. And we get 1.4 times 10 to the negative 3. So again, this here is our H2O plus concentration. So let's just check and see if our x is small works. Because again, for your quiz this week, you still have to show me that you're checking for your x is small, right? For your exam, I'll accept, hey, I know it's going to work. The difference is 10 to the 3. It'll work. But for your quiz this week, I want to see you still checking for your x is small. So I actually want to see you write this piece out right here. So again, our x is small goes our x over our original concentration. And indeed, it worked. And again, we kind of knew it was going to work because the difference, this is 10 to the negative 1, 10 to the negative 4, difference is 10 to the 3. It's going to work. Okay, so now all we need to do is take the negative log of this, and we're all good. So our pH, oops, just ignore this piece, we don't need this piece, is 2.85, just negative log of 1.4 times 10 to the negative 3. Okay, any questions on this? So we can find these values and check if we want to. So here I just found these values. I just subtracted 0.14 minus 1.4 times 10 to the negative 3. You can see, look, it didn't even really change this. I mean, it changed this one by the tiniest bit. So again, what we did when we found that assumption and we said that x is small, we're saying that this change is going to be less than 5%. This one changed so little, the number didn't change. This one barely changed. Barely changed. Again, because our x is small worked. The change was less than 5%. And again, we can check it, throw these numbers back into that equilibrium expression and see, does the number you end up with match the Ka we started with? If yes, then we know our answer is right. Like 100%, we know our answer is right if it matches. Okay, any questions on this? Okay, so if you don't love ice tables, which I'm sure we all love ice tables, there's actually a nice, lovely thing that buffers allows us to do. there's a shortcut where we don't always have to use an ice table. This is called the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation allows us to calculate the pH of a buffer as long as x is small is true, right? So we're still going to need to check out x is small. So we need, the formula is this. So pH equals pKa plus the log of the base over the acid. So conjugate base over our weak acid. Now you don't need to use Henderson-Hasselbalch. It always works with an ice table. You're just going to see how much nicer Henderson-Hasselbalch is. Okay, so if we look, here's our acid. Here's our conjugate base. And again, this Na doesn't mean anything to us, right? That's what we see. That's our conjugate base. And so when we do Henderson-Hasselbalch, we first have to get our pKa. And remember, P means take the negative log of whatever's behind it. So our pKa is just the negative log of our Ka. So we just take the negative log of our K, negative log of our Ka. That is our pKa. And so remember, Henderson-Hasselbalch is just P. Oops. Oh, actually, look, I had it right there. Henderson-Hasselbalch is just the pKa plus the log of the conjugate base over the acid. And so in this case, here is our pKa. There's our, let me try drawing that again, our acid. And here is our conjugate base. And then we just plug in those numbers and we're good to go. So let's just try that really quick. Right, so, and our conjugate base. So when we do that, we get our pH, which is 4.66. Now, we need to make sure, again, Henderson-Hasselbalch only works if x is small. So we need to check if x is small. So if we look at our original concentration is 10 to the negative 2. Our Ka is 10 to the negative 5. X is small should definitely work. But how do you check it? Like, how do you check it? So if I asked you to check this, remember, if this is the pH, you can get to the hydrogen ion concentration. So if you take 10 to the negative 4.66, that's going to give you your hydrogen ion concentration, which is like 2.2 times 10 to the negative 5. That is your H plus concentration. That's your X, right? In your ice table, that's your X. And so remember, what we're going to do is we're going to take our X over our original concentration. Times 100, and we get 0.044%, which is definitely less than 5. Now, we knew our X is small was going to work, again, because this is a negative 2, this is a negative 5, the difference is 10 to the 3, it should definitely work. But if you need to check your X is small, or if you're asked what's the percent ionization, you take 10 to the negative pH. I'm going to put this here. To the negative pH gives you your hydrogen ion concentration. That's what goes on top. Your original acid concentration goes on the bottom. Okay, so let's try another Henderson-Hasselbalch here. Okay, so this problem is exactly the same problem we did before, right? Do you remember this? This problem, right? Our pH, we went through all that work and we got 2.85. Remember this whole thing? Let's do the same thing, This time, let's do Henderson-Hasselbalch so I can show you how different it is. So here's Henderson-Hasselbalch, pKa plus minus the base over the acid. You plug it in, right? Here's our acid. Here's our base. They gave us our pKa. 2.86. See, a lot easier than ice tables, right? And again, this only works for buffers. How do you know if it's a buffer? Weak acid, conjugate base. That's how we know if it's a buffer. Weak acid, conjugate base. That's a buffer. So Henderson-Hasselbalch only works for buffers. You have to have a weak acid and its conjugate base, and X is small has to work. Now, how do we know if X is small is going to work here? Well, we have to figure out the Ka. We have the pKa, right? Or we have the pH. Well, we don't even need that. We have the pH right here. We don't need the Ka. We've got the pH. What am I thinking? So we can't compare it. We could, but we don't have it. So we can compare this. So 10 to the negative that, which is 10 to the negative pH, which is 1.4. And we're going to put that over our original concentration. Or we could have looked at our Ka. Either of those would have worked. And our difference is less than 1. Okay, so we've been talking about, how do you know if X is small works? How are you sure if it's going to work? So now I'm going to go over in detail, how you know if X is small is going to work. Again, for your quiz this week, I want to see the calculation. I don't want to hear X is small works because you write it. For your exam, I'm okay if you just write why it is. But for your quiz, I want to make sure that you show me this X is small approximation. Okay, so how do we know if X is small works? It's true if, number one, the initial concentration of the acid and the conjugate base, or the salt, right? So I'm just going to put acids in here so you can see. So like HF, and the salt, this would be like KF. So really all we care about is F minus, are not very dilute. I know. What does very dilute mean? Like 0.0. Very dilute would be like 0.004, 0.0004, right? So very dilute. And the Ka is fairly small. These approximations, I'm hoping that because of these approximations, you've kind of seen how we do this, right, with approximations. So the initial acid and conjugate should be 10 to the 2 or 10 to the 3 difference. Here, playing with fire. Here, pretty good, right? So the original concentration should be about 10 to the 3 difference of the Ka. And again, if it is this different, these two are true. Usually, right? There are exceptions, and that's why we always check and see using the math piece of it. And so I always say if 10 to the 3, we're safe at 10 to the 3. 10 to the 2, could go either way. Okay. Now, what if, so we talked about buffers. Buffers resist change in pH because it's like Le Chatelier's principle, right? So now what we're going to do is we're going to add a little acid, add a little base, and see how we're going to mess with the pHs now. So how much does the pH of a buffer change when you add an acid or a base? So remember, they resist change, but they still change. So what we're going to do is, this requires a stoichiometry table and a nice little knowledge of Le Chatelier's principle. So we're going to practice this. So we sort of talked about this at the beginning. We're going to practice this using Le Chatelier's principle. So I'm going to read it here, but it's not going to mean anything until we actually do it. So if we add, the added acid reacts with the A minus to make more HA, just like the pictures with the boxes I showed you. If you add a base, it reacts with the acid to make more conjugate. So there's 2 steps. Number 1, it's called a moles table or a stoichiometry table. And that's when we're going to use, actually apply Le Chatelier's principle. And then 2 is using another ice table. Now, a mole table is not an ice table. Not an ice table. Okay, so now, when we see this problem right here, what is the pH of a buffer that has 0.1 mole acetic acid and 0.1 mole sodium acetate, which again, don't care about this, we only care about that, in 1 liter that has, we're adding a base, right? So we're adding a base to this. So this is going to be our acid, our HA, plus OH minus. When we do this, A minus plus water, acid, base, right? So that's our generic equation. Our actual equation is this, but again, it's the same thing. OH minus, A minus, water. Okay, now when we do this, this is a mole table. A mole table is not an ice table. It just helps us keep track of the stoichiometry. So we started with 0.1 moles of this, of our acid, and 0.1 moles of our conjugate. 0.1 moles, 0.1 moles. And we didn't have any OH, but then we added OH. When we add OH, what does Le Chatelier's principle say is going to happen? Which way is this going to shift? Is it going to shift towards the products or the reactants? This is my question for you. Le Chatelier says, will it shift towards the products or the reactants? Come on, you got a 50-50 shot here. I like that comment. What's Le Chatelier's principle? Very nice. Okay, so if we add, remember our buckets? So this is one bucket and this is another bucket. If we have 2 buckets and this one overflows, it wants to go over here to keep them even. So this is going to shift towards the products. So therefore, this is going to decrease and this is going to increase. Because this OH, so what's going to happen? The OH is going to react with the HA to make more A minus, right? HA, A minus. So when we add this OH, it's going to react with all of this, or whatever it can react. And so this is going to go down by the amount of OH we added. So if we added 0.01 OH here, this is going to go down by 0.01. This is going to go up by 0.01. And this is our moles table. So you see how this went up by this amount? And this went down by this amount. So it's applying Le Chatelier's principle. Okay, so this is now our moles table. So this is the amount of our acid and our conjugate base that we have in the end. So this is the amount we've got in the end, right? Well, not in the end, but after we've added our OH. Now we need to figure out our change in our moles. Okay, so OH decreased. This is going to go, so we added this, which means it's going to react with this, and this is going to go up. So I'm trying to do this slow. So this is the amount that went down. This went up by that amount. This is going to go down by that amount. Does everyone see this piece here? Yes? So now in the end, it's 0.1 minus 0.01. This is 0.1 plus 0.01, and now there's none left. So this is the same table we looked at before. I just wanted you to see it again. Now our molarity, remember molarity is moles over liter. Thankfully it's 1 liter. These are moles though. So it ends up being the same, right? Because, well, when you divide it by 1, you get the same answer. Because remember in ice tables, we have to do molarities in ice tables. Okay. So now these are our new molarities, so now we can do an ice table. Or we could do Henderson-Hasselbalch. So let's do an ice table first, just because. So here's our beginning molarities. And again, we have our new reaction. Now, this reaction is our acid. We're going to put our acid in water. And then we have our conjugate, an H3O+. Right? So those are the generic pieces of it. And these are, now we start our ice table. So we have a new piece here. The new piece was that moles table that you just saw. That's our new piece. But now this is exactly the same as what you've done 100 times. Well, maybe not 100 times, but you've done this at least 50 times now, right? This is going to go down. This is going to go up by X, right? This is going to go up by X. Right, we're going to write our equilibrium. We're going to say, hey, X is small, right? The Ka is 1.8 times 10 to the negative 5. We've used this a few times now. We look, this is 10 to the negative 2, 10 to the negative 5, difference of negative 3. Should be good with our X is small. By the way, while I'm doing this, see how many, you can do this using Henderson-Hasselbalch also. Okay, so as we do this one, we assume this X is small, which we know is going to work. We throw that into our equation. And we get, right, so we throw this in, just X is small, cross those off, multiply by 0.09, divide by 0.11 on each side. And we get 1.47 times 10 to the negative 5. Check. This divided by this top box here. Does X is small work? Yes, it does. Right? Then we just need to take the negative log of this because this is H3O+. So we take the negative log of 1.47 times 10 to the negative 5. Sorry, I don't need that slide. And we get 4.83. Okay, that's using the ice table. Let's do this same exact thing doing Henderson-Hasselbalch. So remember, Henderson-Hasselbalch is pKa plus log of the base over our acid, right? I always say it says ba like a sheep. So let's try the same thing. Use the exact same problem we just did. Look, here's the same problem that we just did, straight from the beginning. Wait, where did it go? Sorry, it disappeared. It'll come up. Hold on. One of the slides is just out of order. Okay, so again, here is our equilibrium concentrations, right? Here's our base, and here's our acid. Remember, Henderson-Hasselbalch, we need to have our pKa. pKa is just negative log of the Ka. So we get our pKa, right? We get our pKa, which is 4.75 from our Ka. And that was already given. So negative log of 1.8 times 10 to the negative 5th. That's what gives us our pKa. And then all we need to do is plug in these and we're done. So our base over our acid. So our A minus, I'm just going to go back so you can see. Here's our conjugate base, 0.110. Here's our acid, 0.09. And we get 4.83. Right? So we get the exact same answer pretty much as we did when we did our ice table. So Henderson-Hasselbalch is so much faster. Now, you still have to do that mole table, right? You still have to do the mole table, but you don't have to do the entire ice table. And then we have to check if X is small works. Again, this is our pH. We just take 10 to the negative pH. That gives us our hydrogen ion concentration. We put that over our acid. So over our acid, which was 0.09. And we check. Yes, X is small works. So with your Henderson-Hasselbalch, as long as you know that your X is small works, you can do it. It works with a buffer. And the buffer, again, is a conjugate. It's an acid with its conjugate base. So if you have an acid and the conjugate base, you can do Henderson-Hasselbalch. But you still have to do a mole table, again, if you add any acid or a base. So let's look what happens if we have an acid. So here's the one we just did, right? Just did that, just did this problem. But what happens if we just had NaOH? Look at the difference in the pH. So here in this case, we added 0.01 moles of NaOH to our buffer. And that was the pH, right? That was the pH. Now let's just add 0.01 moles of NaOH to water, right? Our pH is 12. So if you just added NaOH straight to water, the pH would be 12. But if you add NaOH to your buffer, it's at 4.83. Okay. Now, let's see here. So this question, what is the pH of a buffer that has 0.14 moles of HF and 0.017 moles of KF when we add 0.2 moles of an acid? Okay, so I'm going to give you like 4 minutes to try this one, go as far as you can, and then we're going to do this one together. So I want you to try this, go as far as you can, and then we're going to do this one together in just a minute. Like I'll give you like 3 or 4 minutes. Well, I didn't quite get to finish it, or didn't get to finish it, but let's go over how we started. Okay, so we're going to add an acid to our buffer. So when we do that, we have F minus plus H3O plus HF, water. Okay, so I highlighted this in yellow so you can see that. If you're adding a base, then you're going to write the reaction for OH with HA. If you're adding an acid, you're going to write the reaction for H3O plus with A minus. So here's our moles table. So again, here, when we do this, we're adding H3O plus, which means that our HF, right, the H3O plus is going to react with our F minus. So our F minus is going to go down by whatever amount the H3O plus was, and our HF will go up by that amount. So let's look at our moles table. So that means, oh, well, I guess you're just getting the whole thing because it's the only way it's going to work. So again, here's the amount of F minus we started with in our HF. Our HF is going to go, if we add this, the F minus is going to go down by that amount because these two, they're going to react together, creating more of our HF. So if we added H3O plus, it's going to be this is going to go up by that amount. This one goes down by that amount. Right, so that's our moles table. That's what we're doing. So let me put it, I feel like it's easier in the stoichiometry table. So I like to just draw this table. So here's what we did. So we started with point, here's what we started with. That's what we added. This is going to go down by the amount, up by the amount. We added this. This is going to go down. This is going to go up. How much is it going to go up or down? Again, we're going to use all of this. So our F minus is going to go down by that much. Our HF is going to go down by that much. Here's our new moles. With our molarity, it's 1 liter. So it's the same here. It's not always the same here, but it's same here this time because it's 1 liter. Now I'm not even doing ice table. I'm just going to go straight to Henderson-Hasselbalch because I don't want to do an ice table. So if you did that, and we look at our equilibrium here, right? So we have our, here's our HA, and here's our A minus. So we have 0.16 and 0.051, right? So if we did this, this means our pKa, which, did they give us? I think I gave you the pKa in the beginning. Yeah, I gave you, the pKa was 3.15 plus the log of our A minus, which was 0.051 over our HA, 0.160, gives us 2.65. And that is our pH. So it's a little easier than doing an entire ice table, right? A little bit easier than doing an ice table. Again, we're assuming X is small if we're using our Henderson-Hasselbalch. So it definitely takes a little bit of practice. Just as a reminder,